Our voting systems suck. Labour's just winning a landslide 67% of seats on barely a third of the votes. Now, if you don't know, the UK uses a first-past-the-post system where we vote for an MP for our constituency and the winner is the party with the most constituencies. Now, to illustrate one major problem, between Reform and Conservative they actually have more total votes than Labour, despite the fact that combined they have about a third of as many seats. Now, it could be said that Reform split the Conservative vote, as it's likely that a lot of people who voted Reform would have otherwise voted Conservative. And since votes only matter if a party has the most in its constituency, this costs both parties the seat. And we'll refer to this as the spoiler effect, when the existence of a third party impacts the outcome between two others. The US is somehow even worse. If you take a look at the 2016 election real quick, Hillary actually got more votes than Trump. And the US uses a similar system to the UK, where each state is allocated a certain number of electoral votes that usually all go to one candidate, and the candidate with the most electoral votes wins. And again, we see that spoiler effect, where in these three states, the gap between Trump and Hillary is actually less than the number of votes that went to Stein. So if we assume that those votes would have otherwise all gone to Hillary, she would have passed the 270 majority threshold and won. Now, it's a bit mean to blame it on Stein. I blame it on the voting system. Now, both of these are examples of plurality systems, but neither elect proportionally to the vote, and both are highly prone to the spoiler effect. So I just want to explore some alternative systems that might mitigate some of these issues. Now, one proposed alternative is ranked choice voting, where instead of voting for a single candidate, we rank the candidates from favourite all the way down to least favourite. So after everyone has voted for their preferred order, our system will take these total orders as input and output a final ranking. There's a few ways of going forward, but a popular idea is instant runoff voting, which is in use in local elections around the US, as well as some countries like Australia using it for their elections, where we eliminate the candidate with the fewest first place votes and redistribute the votes of anyone who voted for them to those voters' second choice until we have a majority. Just to illustrate, suppose we have three candidates, red, blue and orange, and each dot represents a vote. Under a simple plurality system, orange has done a wonderful job of splitting the red vote. Even though if we extend each dot to a column representing the entire preference, a majority would put blue dead last. Now consider the following votes under instant runoff voting. Each column is a voter. Orange has the fewest first places, so it's eliminated and its votes go to the voter's second choice. In this case red, so red wins. However, look at what happens if a couple of the red voters change their mind and put orange first. Now red is eliminated, its votes get redistributed, and blue wins. Swapping the order of red and orange in a couple of voters has made blue win. And this is precisely the spoiler effect, which we'll formalise in a moment, so we need to keep looking for a better system. Let's do a little exploration into all ranked voting systems. Let's see if we can find one that avoids the spoiler effect. Before we prove anything, it's going to be useful to start with some basic definitions and notation. So suppose this chap, we'll say his mother named him I, well, he ranks red above blue, so we're going to write this. And should red rank above blue in the final outcome, we'll write this. Now, there's a couple of conditions that I think we can agree we'd like our voting system to have. We want what's called Pareto efficiency, which just means that if every single voter agrees, we go with that. Right, the system will never reject a unanimous vote. Like here, they all rank red above blue. Then our system will rank red above blue. Hopefully it's pretty obvious we want this condition. Like this is like bare minimum condition. Second, we want to avoid that damn spoiler effect. And another way of saying this is that the introduction of an irrelevant alternative candidate is independent of the ranking of the others. So for example, orange can place anywhere, but no matter where it goes, it cannot impact the relative order of red and blue. We'll call this condition the independence of irrelevant alternatives, or IIA. We're about to prove Arrow's Impossibility theorem, which just states if you want these seemingly basic conditions, then unfortunately you've got yourself a dictatorship where a single candidate decides the outcome of the entire election. So we'll say some collection of voters G is decisive if in the case where all of G agrees, The result of our election depends only on how the people in G vote and entirely ignores everyone else. So for example here, everyone in G agrees. So for a decisive G, the final outcome is just mimicking G. G can also be decisive over just a given ordered pair, say blue-red, which just means it's decisive over those two and says nothing about orange. And a group G is weakly decisive over a pair, say red-blue, if it is decisive only in the case where everyone else disagrees. Right, so before with decisiveness, it didn't matter what everyone else said, they can agree or disagree. Now we require everyone to disagree, and only then do we go with what G says if G is weakly decisive. So here G is weakly decisive over red-blue. Everyone disagrees, and so we go with G. So we're going to prove Arrow's theorem in two parts. And this result was proven by Nobel laureate Kenneth Arrow. So suppose we have a group of voters G. We'll suppose that G is weakly decisive over red-blue. That is, whenever all of G votes red above blue, and everyone outside of G votes blue above red, then red will rank above blue in the final ranking. Now consider an extra candidate, orange. Our goal will be to show that just by saying that G is weakly decisive over red-blue, we can already say that G is decisive over red-orange. So suppose our G all rank red above orange. Now by IIA, which was that no spoiler effect condition, the final order of red and orange is totally independent of blue. And since right now we only care about how red and orange rank relative to each other, for now we can just suppose that it's ranked like this, where G is putting blue in the middle between red and orange, and everyone outside of G, which is the complement of G we've written as GC, is ranking blue above red and orange, which is totally independent of how red and orange rank relative to each other outside of G. Now by Pareto, since everyone in G and outside of G is ranking blue above orange, we know blue ranks above orange in the final ranking. Now recalling, we said that G is weakly decisive over the order pair red-blue. Well, we've met those exact conditions, right? Where everyone in G is ranking red above blue, and blue above red for everyone outside of G. And hence, red ranks above blue in the final ranking. Now combining those results, we have red above blue, above orange, and by transitivity of a total order, red above orange. But remember, everyone in G placed red above orange, and so G is decisive over red-orange. And to get here, all we supposed was that G was weakly decisive over the order pair red-blue. Suppose instead we'd have G putting orange above blue. Then carrying out the exact same process, supposing red is ranked like this, again we meet the weakly decisive condition. So red above blue, and again by Pareto, orange above red. And so G above blue. So G is decisive over orange-blue as well. Well, look what's just happened. We saw that G being weakly decisive over red-blue meant G was decisive over these two orderings. We can go further. Being decisive over a pair means we're weakly decisive over that pair, right? Since weak decisiveness is just a weaker version of decisiveness, right? Clues in the name. So we can feed these new pairs that we just found G to be decisive over back into the process iteratively. But no pair has any special property. So we can think of this as just swapping the roles of the candidates in the process. So here we're just swapping the roles of orange and red. So now we use weak decisiveness over the pairs we just found and just keep repeating. And by doing so, we find that G is actually decisive over any pair and any ordering between red, blue, and orange. So being weakly decisive over the ordered pair red-blue gives full decisiveness over the pair red-blue, also orange. But orange was just some arbitrary other candidate. So the exact same process shows G is actually fully decisive over everything. So if we just allow G to be weakly decisive over some ordered pair, we've already made G fully decisive over every pair. So we're going to show that if our group G of voters is decisive, then there is a proper subset of G that is decisive. Recall, for decisive G to determine the outcome, everyone in it needed to agree. The result we're about to show would mean that including some of those voters in G was totally unnecessary. So suppose we split decisive G into proper subsets G1 and G2, and let's look at them along with G complement, which was everything outside of G. And just suppose they vote like this in this kind of cyclic pattern. Now since G is decisive, and within G it's agreed that red ranks above blue, then we know that red does rank above blue in the final ranking, and we will use that fact in a moment. Now for red and orange, there are two cases for the final ranking. Either red ranks above orange or orange above red. Now the first case of red above orange, we'll see that G2 and G complement reckon that orange should rank above red, but only G1 thinks that red should rank above orange, and hence G1 is actually weakly decisive over the ordered pair red-orange. Alternatively, if we now recall that red ranks above blue because G was decisive, if G ranks above red in the final ranking, then by transitivity we can combine these, and orange actually ranks above blue, which only G2 had, and hence in this case, G2 is weakly decisive over orange-blue. So G1 or G2 is weakly decisive over some pair. But remember, by lemma 1, that means it's decisive over every pair. So G has a decisive proper subset. Now you might see where this is going. If you remember our Pareto efficiency condition, that said that our system will never contradict a unanimous vote. But another way of saying that is that the entire electorate as a collective is decisive, which means it has a decisive proper subset, which has a decisive proper subset, which has a decisive proper subset. Suppose each region is some collection of voters. Now G' tracks our group of decisive voters. Well, we've just seen it has a decisive subset, so we can shrink G' to a smaller group. But now that has a decisive subset, and that has a decisive subset, and so on. And we can continually iterate this until we arrive at a decisive group of size 1, and that is a dictator. Okay, so we've seen that in any ranked voting system, which is quite a broad range of voting system, the only way to avoid the spoiler effect is a dictatorship, assuming you want Pareto efficiency. Okay, so if we can't avoid it, the next question is how can we mitigate it? After all, Arrow himself said something like, "Most systems are usually fine. All I've proven is that no system is always fine." Well, it turns out there is a type of system that is most spoiler resistant, and those are Condorcet systems. This is where we match each candidate up against each other in a sort of 1v1. If most people rank red above blue, then red will rank above blue. So for example, here most people rank red above blue in a 5-2 majority, so red will rank above blue. Similarly, red ranks above orange, and blue also ranks above orange, and we can combine these to give a final ranking. Now notice, this would seem to completely bypass the spoiler effect, since our ranking between, say, red and blue was totally independent of what orange was doing. But this would contradict Arrow's Impossibility theorem. It is the most spoiler resistant system. But there is an issue. I want you to consider the following set of votes. Between red and blue, blue wins. Between red and orange, red wins. And between blue and orange wins. So we get this rock, paper, scissors thing where they sort of beat each other in a cycle. And this is a Condorcet cycle. So to resolve this, we would need to introduce some other system, and that's where the issue lies. Okay, so other than Condorcet cycles, which are really rare in practice, we do avoid the spoiler effect. So we might wonder, well, in what situations do we avoid the spoiler effect altogether? Imagine simplifying each voter's preference to being single-peaked on a 1D political spectrum. So here we've put the candidates on a left-right spectrum, and the curve represents the voter's preference, so the higher the peak above a given candidate, the higher they would rank that candidate. Now notice, wherever the voter lies on the spectrum, it's impossible to have the middle candidate as your least favourite, since you'll always be further away from some other candidate, right? If you're to the right of red, then you prefer blue, and if you're to the left, then you prefer orange. And so you avoid the Condorcet cycles altogether. Now of course this breaks down if our preferences aren't single-peaked, or when we extend to high dimensions, like a 2D political compass, as we no longer have like a middle candidate. So the cycles re-enter the chat. And whilst we're on it, I'm going to prove a cute little theorem because why not? It's called the median voter theorem, which states that if we arrange our candidates on a 1D spectrum, if our voting system is Condorcet, not only do you avoid the cycles, which we've already seen, but the preferred choice of the median voter is the one that will be selected. So suppose we've arranged our voters and our candidates like this on his political spectrum, and our median voter prefers red. Then if we run our Condorcet process and match red against orange, notice how the voters on his right and the voters on his left will always be equal, since he's the median voter. So since Condorcet methods elect majority winners, those two sides cancel each other out, and he always has the deciding vote. The same is clearly true for red versus blue, and that is the whole proof. Now that's it for ranked voting, but now you might be wondering about other systems. As an alternative to ranked voting, we could consider rated voting, where we give each candidate a score, say, out of 10 for example. Now this is familiar in things like scorecards or Amazon reviews. Now this avoids the spoiler effect, as each candidate is ranked independently, but it doesn't solve every problem. In particular, Gibbard's theorem, which says that even in rated voting, if you have at least 3 candidates, you cannot make the election strategy proof, which means that no system outside of a dictatorship can avoid tactical voting. Now for an example of real-world tactical voting, this YouGov poll shows that half of all Labour voters they polled voted for Labour not necessarily because they wanted Labour, but because it was the best chance of getting the Tories out. Indeed, only 1% voted for Keir Starmer in particular. Now I won't prove Gibbard's theorem, but I just want to illustrate the idea. So again, suppose we have our 3 candidates, and this is our preference where we prefer red to blue, which we really prefer to orange. Suppose the voting system here is a simple majority approval system, where we give each candidate a 1 or a 0, and the candidate with the most votes wins. And for simplicity, there's only going to be a couple other voters, and we'll just say, in the case of a tie, red beats blue, beats orange. If we believe other people voted for each candidate like this, with red having 1 vote, and blue and orange each having 2, then we should give 1 to red only, and hence red wins the tie, and we get what we want. Suppose instead the votes looked like this. We should vote blue, since red can't possibly win. So our vote changed depending on what we thought the others had voted. And if we want to avoid this, then we get back to a dictatorship. So we've seen if you want ranked voting, you're going to run into the spoiler effect. If you try and avoid that, well then you might get a paradox like a Condorcet cycle. Okay, well what about rated voting? Well, you still have tactical voting to worry about. If you want to avoid all of that, yeah, welcome to your new dictatorship. Point is, many of the desirable properties we'd like our voting system to have are actually impossible. And it's surprising to me at least, that we can prove that so simply mathematically. Now having said all that, our voting systems are bad. Like plurality systems are just about the worst by every metric we've looked at today. So we can definitely do a lot better. Thanks boys, this is my first video, so we're only going up. Any questions, drop them below, I'll get on it. Thank you, bye.
Do you have any questions on things that are not related to maths? I'm also fine for those. All fine? Right, okay.